This is lesson 12.1, model inverse variation. You should be on page 765. Recall that two variables x and y show direct variation if y equals ax and x is not equal 0. Now let's review this because we learned this back in, I think it was chapter 4, late in the chapter, what direct variation was. So we should review that right now. Direct variation is slope-intercept form when b is 0. So if I have an equation in slope-intercept form, y equals mx plus b, and the b value is 0, which means it's probably not even going to be written down, it's nothing. If I have an equation in that form, that means that this linear equation directly varies. Now, the book uses a instead of m. I've never, and all books do that, I've never really understood why. We always said m was slope. A is the same thing as the slope. So if you have an equation in slope-intercept form and the b value is 0, that is called that equation is known as directly varying. Okay? A good real-world example of a directly varying situation would be, for example, mowing lawns. Let's say that you can get paid $20 for mowing a lawn. Okay, let me make a little table of this situation. If you mow no lawns, you make no money. But if you mow one lawn, you make 20 bucks. If you mow 2 lawns, you'd make 40, and if you mow 3 lawns, you'd make 60, and so on. Okay, if I plot those points, I'm going to have a linear pattern, a straight line, and if I drew my line, it's going to definitely go through the point 0, 0. The equation for this would be y equals 20x plus 0. So since b is 0, this would be a directly varying situation. So there's a review of what directly varying is. It's something we learned in, I'm pretty sure it was chapter 4. Now, the variables x and y show inverse variation if y equals a over x and a is not equal to 0. So equations of that form are called inversely varying. The non-zero number a, so that means a can't be 0 if it's inversely varying. The non-zero number a is called the constant of variation. So I would get that in your notes. The a value is called the constant of variation. And y is said to vary inversely with x. Tell whether the equations below directly vary, inversely vary, or neither. Okay, so what I need to do is rewrite each of these equations. You notice I have one equation form, y equals mx or y equals ax, and the other equation form is y equals a over x. If I can write any of these in either of these forms, then I would be able to know if they directly vary or inversely vary. So let's do this first one. Let's get y by itself. Let's divide each side of this equation by x. And when I do that, I get y equals 4 over x. Well, does it make sense that that is definitely an inversely varying equation? So this is an inversely varying equation. Let's look at b. I need to get y by itself. Well, to get rid of divide by 2, I can times both sides by 2, which would give me y equals 2x. Well, you notice this equation directly varies because I don't have a b value. This is slope-intercept form, and b is 0. Okay, so that's directly varying. And if you look at c, that's in slope-intercept form, but b needs to be 0 if it's directly varying. b is not 0, so this would be, c would be an example of neither of the prior two types of equation. Why don't you pause the video right now and try those four. Determine if these are directly varying, inversely varying, or neither. Okay, I'm back. So this first equation, it's written in the form y equals a over x. Now, you notice 2 is called the constant of variation. This is inversely varying. Okay, that A value in an inversely varying equation is always called the constant of variation. So number 1 is definitely inversely varying. Number 2, I got to get y by itself. I'll divide by 4, and I get y equals 3/4 x. Now this looks like slope-intercept form, and b equals 0. This is definitely directly varying. That's why I put dv for that one. Number 3, I got to get y by itself, so I'll take away the 5x, and I got negative y by itself. I'll divide everything by negative 1, which gives me y equals 5x minus 3. Now, that's slope-intercept form, but I need b to equal 0, not negative 3 if it's directly varying, so I put n for neither. And this last one, I took y, x equals a half. I divided each side by x. So I have y equals, instead of a half, I just put 0.5 over x. This is definitely inversely varying, and my constant of variation right now is a half. In this lesson, we're going to graph inverse variation equations. So to graph, that's a pretty easy process. You're going to put the equation in your calculator, you'll make a table, and you'll plot points. And you notice this is going to be a curve graph, and you haven't seen one probably like this before. This is probably going to look kind of weird to you and new. When you take this and put it in your calculator and make a table, you're going to get 2 different curves from one set of points. You know, we've never had that happen before where you're getting 2 separate curves from one set of points. So this is going to be new. I'm going to have you sketch these in the next lesson, but for right now, since they're so new to probably most of you, I'm going to have you graph them. So remember, when you graph curves, you're going to probably need to plot maybe upwards of 10, 12 points. If you look in this example in the book, they plotted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They plotted 14 points to get a good idea of the curve. So this is easy. I'll give you graph paper. You're going to plug the inverse varying equation in your calculator. You'll hit table, and you're just going to plot points until you have enough points to get a good feel of the curve. So I don't know that there's much more to say about that here. Graphs of inverse variation equations. This example shows you that as you move away from the origin along the y-axis, so in other words, here's the origin, as you get farther to the right or left, you'll see that this curve keeps on getting closer and closer to the x-axis. But it says it will never cross it. So it's similar to an exponential function that it will keep on getting closer and closer to x but never touch it. As you move away from the origin along the y-axis, so as you move up or down the y-axis, you'll see the same thing happening. This curve will get closer and closer to the y-axis but never touch it. So, in other words, this curve right now is trapped in quadrant 1, and this curve in the bottom left is going to be trapped in quadrant 3. Here's another graphing problem. So again, if you're graphing it, you would take this equation, you'd plug it in your calculator, you'd make a table, and you'd start plotting points, and you're probably going to have to plot, again, 10, 12, 14 points to get a good idea of the curve. Okay? Now, a little note here that's important. The graph of an inverse variation equation lies in quadrants 1 and 3 if A is greater than 0. So let's go back to the previous slide. Let me highlight this. Do you notice how the A value was a positive? If you have a positive A value in inverse variation, your graph will be in quadrant 1 and quadrant 3, which you can see here. But when you go to the next question, do you notice, let me get out the highlighter again, I'll pick purple. This is a negative value, and if you have a negative value for A, the graph will be in quadrants 2 and 4. That's why you see what they have here and here. It's the same looking graph, it just switches quadrants. Here's a general summary of direct variation graphs and inverse variation graphs. Now, direct variation we did back in chapters 4 and 5. Okay? This is just the slope-intercept problem. Do you notice how this says if the slope is positive, your graph should be rising from left to right, and you notice since there's no b value, you have to pass through the origin. So I'm trying to highlight these things as I talk to you. Here they're saying if the slope is negative, your graph should be falling from left to right, and you notice b is 0, so we should be passing through the origin like this picture shows. And then, if you have an inverse variation equation where A is positive, that means your graph should be in quadrants 1 and 3, which you can see here. But if you have an inverse variation equation where A is negative, that means your inverse variation equation is going to have your graph in quadrants 2 and 4, like you see here. Now, these graphs have a name. I haven't used it yet. These graphs for inverse variation, let me take a marker and just point. These graphs are called hyperbolas. So inverse variation equations give us graphs called hyperbolas. Hyperbolas have two symmetric parts that are called branches. So symmetric means, like if I have an imaginary mirror, and let me draw it up here, if I have an imaginary diagonal mirror, you can see that's a line of symmetry. These two sides mirror each other, and these two things are called branches. Now, if A is negative, my mirror is just here. Okay, and you can see where I'm drawing that I have two symmetric branches. Now, the lines of the hyperbola approach but don't intersect are called asymptotes. Okay, so again, this is another vocabulary word, asymptotes. Now, let me take a red pen so you can see them. So you notice we have a vertical asymptote here. Now, the hyperbola will come close to that but actually never touch it, and we have a horizontal asymptote. And the same thing here. We have a vertical asymptote at 0 and a horizontal asymptote. So these right now have asymptotes that are the x-axis and the y-axis. When we do the sketching, I'll actually make you label the asymptotes, but we're not sketching today. We will in the next lesson. Let's use an inverse variation equation. The variables x and y vary inversely. Now let me underline or highlight that because that's important vocabulary. Now think about it. When you read x and y vary inversely, this is what needs to pop up in your head. You need to be saying, oh, that means the equation has to look like that. That's what inversely varying tells me. Okay, now, if y is 6 and x is negative 3, it says write an inverse variation equation. Well, if y is 6, I can plug a 6 in for y. And if x is negative 3, I can plug a negative 3 in for x. And if I can figure out a, I can write my equation. So let's figure out a. Multiply each side by negative 3. A must equal negative 18. Okay, so then I know my equation. If a is negative 18, I just have to go up here and put a negative 18 in for a, and my equation for this would be y equals negative 18 over x. That's the equation that represents this situation. Now there's a part B. Find the value of y when x is 4. Well, that's easy enough. I'll just take x, which is 4. I'll plug in a 4 right here. And I'll take my calculator and do negative 18 divided by 4, and that should be giving me negative 4.5. So if I plug in 4 for x, I get negative 4.5 for y. One thing I should add here that I didn't think about at the beginning of the video, let me give you a real-world situation of an inverse varying equation, a real-world example. Take Halloween and candy. Let's say you go out trick-or-treating. You go on your own and you grab, you trick-or-treat and you get 60 candies. So you go home and you have all 60 candies for yourself. So there would be a point on my table. One person has 60 candies. Well, let's say you decide to call one of your friends and you invite them over and you're so nice, you say, hey, I'm going to let you come over and I'm going to share my candy with you. I'll share it equally. Well, now, because you brought a friend over, there's now two people, you and your friend, and if you share the candy, each of you get 30 pieces. Okay? Do you notice how when you doubled x, doubled times by 2, you doubled x, y became half as much. Okay? What if you said, you know, I'm going to have another friend over. I'm going to have two friends over, so now there's 3 of us. Well, if there's 3 of you sharing 60 pieces, you're now down to 20 pieces. So look here. If you triple x, y has now a third as much. Or what if you had 4 friends over? If you quadruple x, you have to take 60 and you got to multiply it by a fourth. That means each friend, including yourself, would get 15 pieces. And I'll do one more. If you had another friend over and it's 5 people, if you multiply by 5, then you'd have to take a fifth of 60, which is 12. Okay, so every time I increase x by a certain amount, y is going to inversely vary. So that would be a good real-life example of what we would mean by inversely varying. Okay? Let's have you try this. I want you to try to write an equation for this situation. Pause the video and do it. Okay, I'm back. So first of all, did you notice that they tell you x and y vary inversely? Well, if that's the case, my equation has to look like that. I'm circling it. Okay, y is -2 and x is 12. So where you see y, plug in -2. You can see I did that here. And where I see x, I'll plug in 12. And now to solve that, multiply each side by 12 to get a by itself, and I'll figure out that a is -24. Well, now that I know that a is -24, I can plug -24 in for a, and there's my equation, y equals -24 over x. Now they do ask me to do one more thing. Now find the value of y when x is -3. Well, that's simple. I'll just take -3. I'll plug it in right here for x, and if I do that, if I plug a -3 in for x, -24 divided by -3 means y is 8. So -3 for x would give me 8 for y. Now, let's talk about writing an inverse variation equation by looking at a table. Now, we've had to do tables in this chapter. You've had to tell me if you can tell if a table's linear, exponential, or quadratic. Now, here's another one. You've got to be able to tell me if a table's inversely varying. Now, this is pretty easy to do. In fact, it might be the easiest of the 3. If a table inversely varies, it means that a set of ordered pairs are showing inverse variation if all the products are constant of x and y. So that's the key part here. Let me read that again. Inversely varying tables have x, y products that are constant. Now, what does the word product mean? I hope you're thinking, oh, that means multiply. Okay, so look, let me highlight these. If I multiply -5 times 2.4, you can use your calculator right now, you get -12. If I multiply -3 times 4, I get 12. If I multiply 4 times -3, I get -12. If I multiply 8 times -1.5, I get -12. Do you notice how when I multiply x and y, I keep on getting the same thing? That means that this is an inversely varying table, which means it's an inversely varying equation, which means it has to be written like that. And the constant of my variation, I'm finding it out every time. If I multiply x and y together, I keep on getting 12. So a must be negative. I meant to say -12. So a must be -12. So there's my equation. Okay, so this should be the easiest of the tables to find. So if it's not a linear table, if it's not exponential, if it's not quadratic, it could be inversely varying. If you multiply x and y and get the same thing every time, it is inversely varying, and what I get is my a value. They will have you solve some multi-step problems. Now, when you read these things, here's the key point again. When you read this carefully, look what it says here. The work time varies inversely. Well, as soon as I see that, I know that it's got to be an equation of that form. Now, instead of y and x, that's an x there, instead of y and x, they're using t and p. So t varies inversely with p. So that means t varies inversely with p. They tell me that the company estimates 25 people, so that would be p, working for 300 hours, that would be t. So you notice they put 300 in for t and 25 for p. And now we can figure out what a is. If I quickly multiply each side by 25, I'll find out a is 7,500. So there's my equation. T equals 7,500 over p. And now, here's the last part of the problem. Now that I have my equation, let me highlight that equation. Now that I have that, find the work time per person if the company hires 30 people. Well, all I got to do is plug in a 30 for p, take 7,500 divided by 30, and that would tell me if we hire 30 people, the work time would be 250 hours per person. Before we quit the video, you go ahead and try this. Determine if these ordered pairs inversely vary or not. Okay, and you should have been coming up with when you multiply these two together, you get negative 10. When you multiply those two together, you're getting negative 10. When you multiply those together, same and same here. These definitely inversely vary, so I'm getting the same thing, and the equation must have been that. Okay, there's my inversely varying equation. I'm going to pause the video here. If you have questions, make sure you ask in class.